Water everywhere, but not a drop to drink. That's the paradox of our planet. Oceans cover over 70% of Earth's surface, but seawater is salty and unsafe for human consumption. So how do we turn this vast, undrinkable resource into clean, fresh water? Today, we're diving deep into one of the most incredible processes of modern engineering, desalination, the method that turns seawater into potable water. Let's follow the journey of a single drop of ocean water as it travels from the sea to your faucet. In many regions around the world, like the Middle East, parts of Africa, California, and Australia, freshwater supplies are dwindling. Population growth, climate change, industrial demand, all these factors put pressure on our natural freshwater sources. To fill the gap, countries are investing in desalination plants, massive facilities that convert salt water into safe, drinkable water for homes, farms, and industries. There are over 21,000 desalination plants operating worldwide, producing more than 100 million cubic meters of potable water every day. But how does it all work? The process begins right here, at the intake station. Massive pipes draw in seawater directly from the ocean. But this isn't just a straw in the sea. There's high-level engineering behind it. The intake is designed to minimize harm to marine life. Screens and filters block out fish, seaweed, and debris. Only water is allowed in, millions of gallons every day. From here, the water is pumped into the facility for the first phase of treatment. Before we can remove the salt, we need to remove the junk. That's where pretreatment comes in. Seawater contains suspended solids like sand, silt, algae, and even tiny microorganisms. Through a combination of mechanical filters, chemical dosing, and microfiltration membranes, the water is cleaned of particles that could clog or damage the high-pressure systems used later. Pretreatment is critical. If it fails, the whole system can shut down. Once the water is clean enough, it's ready for the most important step. Now we come to the heart of the process, reverse osmosis. This is where technology meets nature and flips it. Under normal osmosis, fresh water naturally moves through a membrane to dilute salt water. But in reverse osmosis, we do the opposite. Powerful pumps force seawater through special membranes that are so fine, only water molecules can pass through. Salt, minerals, bacteria, viruses, they all stay behind. It takes 600 to 1,000 psi of pressure to push the water through. What comes out on the other side? Pure, clean water. The salty waste called brine is separated and dealt with separately. For every gallon of fresh water produced, there's about half a gallon of brine. This super salty waste can't just be dumped back into the ocean recklessly. Brine is carefully diluted and discharged through special outfall systems that disperse it over large areas. Environmental agencies monitor the temperature, salinity, and ecological impact to ensure local marine life is protected. Newer technologies are also exploring how to reuse brine for salt recovery, industrial chemicals, or even as a source of valuable minerals like lithium. While reverse osmosis removes the salt, it also strips the water of essential minerals. So before the water can be sent to your tap, it must go through post-treatment. Engineers remineralize the water by adding calcium and magnesium, essential for taste, bone health, and pipe protection. Sometimes, a small amount of chlorine or UV treatment is added to ensure safety during transport and storage. Then the water undergoes rigorous quality testing to meet international and national drinking water standards. Only when it passes every test does it move on. Now the water is ready for delivery. Pumped through miles of underground pipes stored in water towers or injected into the existing municipal supply, this once salty seawater is now safe, clean drinking water. It fills bottles, feeds crops, quenches thirst, and in many coastal cities, it makes up a significant portion of the total water supply. Desalination is powerful, but it's not perfect. It's energy intensive, expensive, and has environmental impacts. But innovation is rising to the challenge. Solar-powered desalination, nanotechnology membranes, and zero liquid discharge systems are changing the game. New plants are more efficient, smaller, and more sustainable than ever before. In the future, we may see portable desalination units, disaster relief systems, and even desal plants aboard ships and space stations. As freshwater grows scarcer, desalination offers hope. It taps into a resource we have in abundance and makes it drinkable. But like all powerful tools, it must be used wisely, balancing innovation with conservation, sustainability with scale. In a world where water is life, desalination is not just a technology, it's a lifeline. This is just one of the many incredible processes we uncover. So if you're curious, inspired, or just love great storytelling, subscribe now and ring the bell so you never miss what's coming next. Beneath the Earth's crust, hidden in ancient volcanic formations, lie some of the most prized treasures known to mankind. Diamonds. For centuries, these shimmering stones have captivated royalty, industries, and investors alike. But their story begins long before they ever reach a jeweler's display. The history of diamond mining stretches back over 2,500 years to ancient India, the first known source of diamonds. These early gems were found in riverbeds and traded along the Silk Road, believed to bring strength, invincibility, and spiritual clarity. By the 18th century, Brazil had become the world's largest supplier, before the discovery of massive deposits in South Africa changed everything. In 1867, a young boy found a shiny stone along the Orange River, a 21-carat diamond that sparked a modern diamond rush. This led to the founding of some of the world's most famous mines, including Kimberley, home to the legendary Big Hole. Today, diamond mining is a high-tech global enterprise. The world's largest mines span across continents, from Jwaneng in Orapa in Botswana, to Mirny in Russia, Venetia in South Africa, and Diavik in Canada. Some operations reach depths of over 1,000 meters, and each year, more than 130 million carats of rough diamonds are produced globally. But how are these tiny crystals of carbon extracted from solid rock? And what does it take to bring them from the Earth's core to the world's most exclusive boutiques? Join us as we journey deep into the heart of modern diamond mining, a world of massive machines, precision science, and sparkling ambition. Geologists use satellite imaging, geophysical surveys, and soil sampling to identify promising sites. Once a potential kimberlite deposit is located, it's drilled and sampled to assess the concentration of diamonds. This process can take years and millions of dollars in investment before a mine is approved. Only a small percentage of kimberlite pipes actually contain diamonds in commercially viable quantities. If one does, the project moves into the development phase. In open-pit operations, huge amounts of overburden, layers of soil and rock, must be removed. The process begins with explosives, followed by massive hydraulic shovels and dump trucks that can carry up to 400 tons of rock at a time. This material is hauled to the primary crushing stations, where the hard kimberlite rock is broken down to manageable sizes for further processing. Once the ore is brought to the surface, it enters the primary crushing phase. Here, giant jaw crushers reduce large rocks into smaller pieces. The material is then passed through secondary and tertiary crushers to reduce it even further. By now, it resembles gravel-sized particles. The goal? To liberate the diamonds trapped within the rock matrix. From here, the crushed ore is sent into a washing and screening circuit to separate fine particles and slurries. These finer materials are essential because diamonds are often only a few millimeters in size. Next, the slurry moves through dense media separation tanks, where materials are separated based on their density. Since diamonds are extremely dense, they sink to the bottom, while lighter waste material floats. The diamond-bearing concentrate is now ready for recovery. But finding these tiny gems in tons of rock still requires a highly specialized process. Now, the real treasure hunt begins. The diamond-rich concentrate is fed into X-ray fluorescence machines which detect the unique light refraction of diamonds. When a diamond is identified, a jet of compressed air precisely ejects it from the conveyor belt into a separate container. This method is remarkably effective, recovering over 98% of diamonds in a single pass. Recovered diamonds are still raw and coated in grime. They undergo acid cleaning to remove any residue from surrounding rock. At this stage, they're referred to as rough diamonds. Next, the diamonds are hand-sorted into various categories based on size, shape, color, and clarity. This step is done by trained gemologists who evaluate thousands of stones each day. Industrial-grade diamonds used in tools and cutting equipment are separated from gem-quality diamonds, which move on to valuation and certification. A single mine can produce up to 10 million carats annually, but less than 25% will be suitable for jewelry. The rest are used in lasers, drills, and grinding equipment. Every diamond is registered, tagged, and documented for traceability, ensuring ethical sourcing and conflict-free certification, a process now mandated by the Kimberley process. Once sorted and certified, rough diamonds are packed in secure, tamper-proof containers. These are shipped to international trading hubs like Antwerp, Dubai, or Mumbai, where they enter the global market. Auction houses and diamond companies bid on lots worth tens of millions of dollars. Once sold, the diamonds are sent to cutting and polishing centers in India, Israel, or Belgium. There, artisans use lasers and high-speed rotary tools to cut each stone with mathematical precision, maximizing brilliance and carat weight. A rough diamond may be cut into one or several polished stones, depending on the original size and quality. Each cut is planned in 3D software before any physical shaping begins. Finally, the polished diamonds are graded by labs such as GIA or IGI, receiving their official certification that includes the famous 4 C's: cut, color, clarity, and carat. From mine to market, the journey of a diamond can take months, sometimes years. But every sparkle begins with one thing: rock moved, sorted, and refined through one of the most sophisticated mining operations on Earth. More than just sparkling gemstones, diamonds represent a fusion of Earth's deepest secrets and human ingenuity. From volcanic pipes to laser-guided polishers, their path is paved with geology, engineering, and skilled craftsmanship. But today's diamond industry is also increasingly focused on responsibility, minimizing environmental impact, ensuring fair labor practices, and building transparency through blockchain and digital tracking. Massive diamond mines employ tens of thousands of people and contribute billions to local and national economies. Yet, each carat extracted also comes with a responsibility to protect the land, the people, and the legacy these gems will carry into future generations. The next time you see a diamond glint under the light, remember, it's not just a symbol of love or luxury. It's the result of science, technology, global effort, and a journey that spans millions of years beneath our feet. Every year, the world discards hundreds of millions of smartphones, each filled with tiny components that are no longer useful to us, but hold an unexpected treasure. Inside these outdated devices lies gold, not metaphorically, literally. Microscopic traces of the precious metal coat circuit boards, connectors, and chips, giving us an opportunity to extract incredible value from what we usually throw away. In fact, 1 ton of used mobile phones contains more gold than 1 ton of mined gold ore. But how do we recover it? What kind of technology, precision, and chemistry are involved in turning tech trash into 24-karat treasure? Today, we step inside a high-tech recycling facility where discarded mobile phones undergo a meticulous process to extract pure gold, using chemistry, fire, and cutting-edge machinery. This is industrial recycling at its most precise and valuable. This is how 24K gold is made from e-waste. Our journey begins at a centralized e-waste collection hub, where discarded electronics from around the country are gathered. From urban drop-off programs and corporate tech recycling to bulk shipments from phone retailers, the waste arrives in containers, stacked high with smartphones, tablets, and other compact electronic devices. Each of these devices contains minute quantities of precious metals, but first, they must be sorted. Workers at the sorting facility wear protective gear and begin the initial separation process. The outer plastic casings are removed, and lithium batteries are extracted to be handled separately due to fire and explosion risks. The real prize lies inside, the printed circuit boards, or PCBs. These are the green or blue slabs that house microchips, capacitors, and gold-plated connectors. Each PCB contains a fraction of a gram of gold, but when you have thousands of boards, the numbers add up fast. Circuit boards are collected into large plastic bins, while other parts, screens, plastic, and aluminum, are sorted for their own recycling streams. The PCBs are loaded onto a conveyor belt that feeds them toward the material reduction phase. But before they get shredded, any remaining components, such as glass chips or magnetic drives, are removed. This ensures a clean feed and helps prevent contamination in the later chemical stages. This pre-sorting stage is both manual and mechanical. While human workers perform delicate separation tasks, larger mechanical arms and automated trays assist with bulk movement and categorization. Every single action is documented and logged, not only for quality assurance, but for environmental regulation and traceability. This gold extraction process is highly controlled, as it involves both valuable materials and hazardous waste. With the non-essential parts removed and the boards carefully sorted, we now move to the next stage, grinding them down into something far more manageable. Once the printed circuit boards have been sorted and stripped of hazardous parts, they enter the second phase, shredding and material reduction. The goal here is simple: transform bulky boards into fine particles, increasing surface area and making it easier to separate metals later on. The conveyor belt feeds the PCBs into an industrial shredder. This massive machine is fitted with rotating steel blades capable of pulverizing hardened materials. Within seconds, circuit boards are reduced to tiny fragments no larger than a grain of rice. The resulting material, often called e-scrap granulate, is collected in large bins. But this mix isn't just gold. It's a chaotic blend of metals, resins, fiberglass, and microscopic dust. Now it's time to separate the components. First comes magnetic separation. A spinning drum lined with magnets pulls out any ferrous materials, such as leftover screws or steel connectors that survived the shredding process. Next is the eddy current separator. This high-speed rotating system uses magnetic fields to eject non-ferrous metals like aluminum and copper from the conveyor stream. These lighter metals are pushed into separate bins for recycling. What remains is the real target: a high-density mix of non-magnetic materials, including gold, silver, palladium, and platinum, all still attached to fiberglass and resin dust. The dust is passed through vibrating screens and cyclone separators, which sort particles by size and density. Larger chunks are re-shredded. Finer, more homogeneous particles move forward. Throughout this process, powerful vacuum systems remove harmful airborne particles, sending them through activated carbon filters to trap toxins. Safety and environmental compliance are paramount. After all, this isn't just valuable, it's volatile. By the end of this stage, the factory is left with bags of fine powder, black, gray, and occasionally speckled with metallic glints. Hidden in this unassuming dust is the gold we're after. But separating it from the rest of the material isn't just a matter of filtering. It requires precision chemistry and one of the most powerful reagents in modern metallurgy. The shredded circuit board powder is now ready for the heart of the operation, chemical extraction. And the star of this phase is one of the most powerful reagents known in metallurgy: aqua regia. Aqua regia, meaning royal water in Latin, is a highly corrosive mixture of nitric acid and hydrochloric acid. typically in a 1:3 ratio. This golden yellow solution has a unique ability. It can dissolve gold, a metal resistant to most acids. In sealed chemical reactors, the fine e-waste powder is carefully mixed with the freshly prepared aqua regia. The tanks are made of reinforced materials resistant to corrosion, and the process is fully enclosed to protect both workers and the environment.